You hear it all the time, right? That modern AI is basically a digital copy of the human brain. It's a really powerful idea. But is it actually true? Well, today, we're going to look past the hype and see what neuroscience has to say about our most advanced tech.
So, right off the bat, just looking at the blueprints tells you a whole lot. Over on the left, you've got a typical deep learning network. See how clean and linear it is? It's basically a one-way street for information. But then you look to the right, and that's the cerebral cortex. It's a dense, tangled, chaotic-looking web. The difference is pretty stark, isn't it? Structurally, they couldn't look more different.
But, this whole comparison didn't just come out of nowhere. For a while, some really smart researchers were pretty much convinced that AI had cracked the code of the brain. And that's because there are some similarities that are, well, pretty seductive.
And you can totally see why they thought this. I mean, both systems seem to process things in a series of layers, right? A hierarchy. And the little nodes in an AI, they develop these response properties that look uncannily like the neurons in our own visual system. And let's be real, both are ridiculously good at recognizing patterns. So it's easy to see why people thought, yep, that's it, we've done it.
But this is where the simple, neat story starts to fall apart. Are these similarities on the surface really the whole picture?
Yeah, not even close. Turns out our standard AI models are missing 4 absolutely crucial, fundamental features that really make the brain, well, the brain. Let's break them down.
First up is something called massive recurrence. Just look at that number. About 80% of the connections in the cortex are reciprocal. This is no one-way street. The brain is constantly creating these feedback loops, talking to itself, refining and processing information in a complex, ongoing dance.
Second, our brain circuits have this natural tendency to oscillate. They're not just sitting there passively waiting for a signal. They have a built-in rhythm, like a constant hum or an engine that's always idling, ready to engage in these incredibly complex dynamics at a moment's notice. And third, adaptive synapses. The connections in our brains are not set in stone. They're constantly changing based on what we experience. This is that classic neurons that fire together, wire together idea. The brain is physically rewiring itself, moment by moment, to reflect the patterns of the world around it. It's building a model of reality into its very structure. And finally, we have the temporal dimension. And this is a really big one. For the brain, when a neuron fires is just as critical as if it fires. It uses the precise timing, the synchronization of these signals, to encode relationships between things. Time itself becomes a language, a whole other dimension of computation that most AI models are just completely blind to.
So you might be wondering, okay, 4 differences, so what? Well, it turns out they matter an enormous amount. It all comes down to solving one gigantic problem, and it reveals the brain's secret to being so incredibly efficient.
Just think about it for a second. The world is filled with a practically infinite number of combinations of objects, features, and relationships. How can any system, whether it's biological or artificial, possibly keep track of all of that without just running out of parts? This really shows the 2 different game plans. On one hand, you have AI's labeled lines approach. It's rigid. It basically needs one specific neuron for every single possible combination. You can see how that leads to what's called a combinatorial explosion. You'd run out of hardware almost instantly. But the brain is way more clever. It uses what are called dynamic ensembles. It creates these temporary teams of neurons that fire in perfect synchrony to represent a relationship, and then they disband. It's flexible, it's efficient, and it's basically limitless.
So, to put it simply, the brain found a cheat code. It escapes the physical limits of its hardware by jumping into the dimension of time. It uses timing and synchrony as a language to create infinite meaning out of a finite number of neurons. Pretty smart.
Okay, so this all sounds amazing in theory, right? But does any of it actually work in the real world? Well, a group of researchers decided to put these brainy principles to the test in a simulation.
So what they did was they took a standard AI network and gave it a biological makeover. They made the nodes act like those oscillating brain circuits, they put in time delays for the signals, they made the connections adaptive so they could learn, and they even pre-trained it just by showing it statistical patterns, kind of like how a baby learns about the world.
And the results were, well, they were staggering. The new brain-inspired network learned the task in a tiny fraction of the training steps that state-of-the-art AI models needed. We are talking orders of magnitude faster and more efficient. It wasn't even close.
But that's not all. It was also way more robust. See, when the data got messy and noisy, which, let's face it, the real world is, the standard AIs started to fail. But the brain-inspired network, it just kept on performing exceptionally well.
So, what's the big takeaway from all of this? Well, it points to a fundamentally different way of thinking about computation itself. A whole new paradigm that isn't based on digital ones and zeros, but on the analog dynamics of the brain.
And neuroscientist Wolf Singer just puts it perfectly. He says, in essence, it's an analog computer. It has nothing to do with the artificial network systems that we know. It's a radically different strategy. This isn't just a small tweak. It suggests we've been building a completely different kind of machine all this time.
And what he means by that is this. Your brain doesn't think in discrete ones and zeros like your laptop does. It computes with these continuous, high-dimensional, dynamic patterns of waves and oscillations. Think less like flipping billions of tiny switches and more like calculating the complex interference patterns of waves in a pond.
Which leaves us with one last, really big question to chew on. If the most efficient, powerful, and robust computer we know of, the one sitting inside our own heads, isn't digital at its core, should the future of artificial intelligence be?